All right, so I'll just do this last problem that I didn't do on Monday, and then we'll just answer questions. If you have anything in particular that you want me to go over, I'll just go over that. So for this last problem, I have to say there is one problem at the end that uses a little bit of the Saeta, but it's much simpler than this one. So if we can do this one right now, then the one in the exam should be a lot simpler. So consider the quadrilateral element shown in the figure. The quadrilateral is defined in terms of the XY domain, but then there's also the psi eta triangle. And the element is made out of 4 nodes. The shape functions are given. And then we are asked about the XY coordinates of the point that has in the psi eta coordinates. So we want to know there's a point here that is the minus 0.5. Oh, sorry, not that point. This point right here. So that point right here has coordinates minus 0.5, 0.5 in the psi eta. And we want to know what are the corresponding XY coordinates. So that point will go somewhere over here, and that's what we are asked. That is part A. Then we want to get the Jacobian at that location. So we want both the X and the Jacobian at that location, and then we want to evaluate the gradient. So let's do A and B first, and then I'll go back to C. So for A and B, I just need to evaluate the isoparametric map and the Jacobian. What is the definition of the isoparametric map and the Jacobian? I have extra space here. So the isoparametric map is just the X vector is gonna be the sum of the shape functions evaluated at psi eta times the nodal coordinates. And I just do it with the vector notation. So these are X and Y components. So this will mean if you want to put it in sort of X, Y components, so the X and Y components are going to be the sum of the shape functions. So the first shape function evaluated at the psi eta, and we want it evaluated at psi minus 0.5 eta 0.5 times the XY of the first node, which is, let's see, the first node is here, so 2, 2. So 2, 2 plus N2, I'm just gonna skip a little bit of notation, I'm just gonna say minus 0.5, 0.5 times the second nodal coordinates, which are 1.52 plus the third shape function evaluated at minus 0.5, 0.5 times the third nodal coordinates, which are 1, 1, and then plus the fourth shape function evaluated at minus 0.5, 0.5, and then times the nodal coordinates 2, 1. So again, this is nothing but the definition of the isoparametric map, sum of the shape functions evaluated at the corresponding psi eta times the nodal coordinates. So we can do that. So this one would be the first shape function at minus 0.5, 0.5. If we go here to the first shape function, we need to evaluate this at minus 0.5, 0.5. That is going to be, so 1 minus 0.5, that's 1.5. And then, so 1.5 times 0.5 over 4. I think it's 1.5 over 8. So 1.5 over 8 times 2. The second one is going to be, so now 1, so this one is 0.5, 0.5. So I think it's 1 over 16. Yeah, I'm doing it correctly. Trying to do it on the go. 1 over 16. Then the next one is 0.5 times 1.5. So it's similar to the other one. So 1.5 over 8 times 1, and then the last one is 1.5 times 1.5 over 4. So 1.5 square over 4. 1.5 square over 4 to 1. Hopefully I didn't make mistakes. And then if someone can tell me what this is, I'd appreciate it. .3 and 3.69. Hopefully that is probably not true because that seems like it's outside of the, maybe I made a mistake in the, okay, that sounds more like it. 1.41 and what? Okay, let's see, 1.41 and 1.06. Does that make more sense? Yeah, that makes more sense. 1.41, 1.06. So it should be, I mean, if you can see here that we are closer to the 4 here, we should be closer to the 4 here. So it should be somewhat closer to the 2, between 1 and 2, probably 3/4 of the way. And between the 1.06 sounds a little bit low, to be honest, but the 1.41 sounds correct. I'm not completely sure about the 1.06. That seems very, very close to the bottom of the quadrilateral. But you know, pending errors in the calculation, hopefully the process is correct. I don't know if I made the mistake evaluating one of the shape functions. Did I make a mistake? Okay, that sounds more like it. 1.7 what? Okay, that makes more sense. Yeah, the 1.06 was too close to the bottom. Okay, so any questions about the process though? Evaluating the shape functions are the corresponding psi eta, and then evaluating the isoparametric map is shape functions times nodal coordinates. Good, all right, so that's A. Now for B, we need to evaluate the Jacobian. And then I probably gave the, did I give the definition? Yes. So the Jacobian is this matrix that will have dx, d psi, dy, d psi, dx, d eta, dy, d eta. And then if you go to the notes, this is basically the derivative of the isoparametric map. So because in the isoparametric map, we have the sum of the shape functions times the nodal coordinates. Here, what we will get is for each one of these, we'll have, again, a sum of the, now not the shape functions, but the derivatives of the shape functions. So the derivatives, and for example, for the top row is going to be the derivatives of the shape functions with respect to psi times the x coordinates, sum of the derivatives of the shape functions with respect to psi of the y coordinates, sum of the derivatives of the shape function with respect to eta, sum of the derivatives of the shape function with respect to eta, but of the y coordinates. So that's what we need to do. Now, to evaluate that, I need those derivatives. So dn1 d psi. That one is 1/4 1 minus eta. Just, yes, that is correct. Then dn1 d eta is gonna be 1/4, oh, minus, probably minus 1/4 minus 1/4, no, plus. Wait, which one? Check, is it 1 minus eta? Okay, minus, so I need a minus here. And then minus 1/4 1 minus psi. And we need to evaluate that at minus 0.5. So evaluate at minus 0.5. This is going to be minus 1/4 minus 1/8. Right, so 1 minus 0.5 and then times minus 1/4. And this evaluated at minus 0.5 is going to be minus 1.5/4. All right, so that's the first one. Then the second one, the derivative with respect to psi is going to be plus 1/4 1 minus eta, evaluated at minus 0.5. That is going to be 1/8. Then derivative with respect to eta is going to be minus 1/4 1 plus psi, evaluated at minus 0.5 should be minus 1/8. Then derivative of n3 with respect to psi is 1/4 1 plus eta, evaluated at minus 0.5. That should be 1.5/4. I really hope I'm not making mistakes here. This is 1/4 1 plus psi, evaluated at minus 0.5. That is 1/8. And then the last one, this is minus 1/4 1 plus eta. That's minus 1.5/4. And then is 1.5/4. So again, take derivatives with respect to psi eta and then evaluate at the corresponding point. Now, given this, I can actually go back and let me copy this. Shrink this. Okay, so sum of the derivatives with respect to psi times the nodal coordinates. So this one will be minus 1/8 times the first nodal coordinate, which I think was 2, and then plus 1/8 times the second nodal coordinate, the x component. So let me see, 2, 1.51. Okay, 2. Then plus 1.5/4, 1.5, and then plus minus 1.5/4 times 1. So this one is each of the derivatives with respect to psi times the x coordinate. Then all the same, but with the x coordinates. So let me copy this and paste it here, but now I'm gonna delete all of these. And let's put the y coordinates. And the y coordinates are 1, 2, 2, 1. 1, 2, 2, 1. 1, 2. For the bottom, now I need all the derivatives with respect to eta. So I need this, 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 and this. So minus 1.5 over 4 times 2, then minus 1/8 times 2, then plus 1/8 times 1.5, and then plus 1.5 over 4 times 1. And then here, the same functions, but now I just need to change the coordinates and do the y coordinates instead. So 1, 2, 2, 1. The exam is much less computations than what I'm doing here. And so hopefully you can evaluate that, and then you can tell me what the 4 components are. And as a side note, you can do this in MATLAB. I'm fine if you solve the exam in MATLAB, perfectly fine, as long as you put the screenshot of your, or Python, as long as you put the screenshot of your code, the equivalent of this. I want to see your work, but it can be by hand or it can be in code. I don't mind either way. They have the answer for this one. If I was doing it, I think I would do it with, I would just code it.
When you say you can just code it, did you include where we get to find stiffness matrix and this kind of stuff?
I mean, for this question, it depends on the question. But so anything that is asked for in the exam, I want to see your work. But your work can be code. So if you have coded something, you can show the code, a screenshot of the code. I'll take that. I don't want to see your code, your work, basically. So whether it's done with code or by hand, I'm fine with that. Yes. And I was going to say, as you're doing that, I don't know if I have done this in. It only has the. I'll switch over from here, and that is a little bit. How do I do this so that it appears on the? Okay, let's see, how do I do this? I want to show you the code. How would I code it? So I want to show you that. Let me stop screen sharing here. stop broadcasting that. And then what I'll do is here. Hopefully, there's no echo. There's no echo. Good. All right. So I will share my screen here. All right. So if I were to code this, how would I code it? For the quadrilateral elements, they are in Python Lab 6. So we haven't done that. We'll do that on Friday. But you could go to the Python Lab 6 if you needed the quadrilateral shape functions. So I just copy this type of thing. This you don't need to remember. But I just show you how I would do it because I don't like writing that much on the, you don't need that. What you need is this, right? So what you need is basically the shape functions and the derivatives. This one you can either code, or if you go to the material on Brightspace, the Python Lab 6 has the quadrilateral shape functions. So if you needed, the Python Lab 5 should have, I think 4 and 5 have triangular shape functions, and then 6, which we'll do on Friday. But if you need to have already the coded shape function, you can just go to Python Lab 6. And you can see that this is nothing but the definition that I just had, right? So the first shape function takes in psi eta and it evaluates a quarter of 1 minus psi, 1 minus eta. And then I've done the derivatives. So you can just see that these are the corresponding derivatives with respect to psi eta. And that's really all I need. And then with that, now I can do my, this is how I would do it. So x1 is 2, y1 is 1, x2 is still 2, y2 I think is 2. Then x3 is 1.5, y3 is 2. And then x4 is 1, and y4 is 1. I think that is correct. So these are the xy coordinates. And so if I want to evaluate the isoparametric map, this x is the sum of, let me do it in comment. So x is the sum of the shape functions evaluated at minus 0.5, 0.5 times the xi. Let me do x sub I, right? And then the y is the sum of the same shape functions evaluated as minus 0.5, 0.5, but times the y coordinates. So I just need to evaluate first shape function at minus 0.5, 0.5 times the first x coordinate, and then just copy paste this. And then just change, okay, second shape function with second x coordinate, third shape function with third x coordinate, fourth shape function with 4x coordinate. And then the y is everything, same shape functions, but just the y coordinates. Something is wrong because do I have the incorrect? I'm printing x twice. Good one. I'm like, this doesn't make sense. There we go. But this is still not correct, right? So this is should not be 1.34. So I think this x4 maybe is not 1. Let me see. Oh yeah, x4 is not 1. Where is the? Just check, but so the x are. Oh, I made it wrong. So x1 is 2. Probably made the other one wrong as well. So 2, 2, then 1.52. Okay, so this is 1.52. Then 1, 1. And then 2, 1. There we go. Okay. So it was 1.06. Did I make this correctly? So no, 2, 2. Oh, there we go. That was your mistake. There we go. There we go. Exactly. I think I would do it like this. So if you show me this, if you take a screenshot of this piece of code, with yeah, if you show me basically the fact that you have the shape functions and that you just have the xy coordinates and then you're just evaluating the isoparametric map, that works as good as by hand. Any questions about doing it with code? Okay, for the Jacobian, again, I think I would just do it with code. And so here, I just do the same, but now we'll replace. So the first entry, instead of the shape function, I need the derivative. So I did need dn1 d psi, dn2 d psi, dn3 d psi, dn4 d psi. That is the first entry. Then the second entry is going to be the same, but with the y coordinates. So this one is going to be the same, but with the y coordinates. And then the second row is going to be the same, but it will have eta. So derivative with respect to eta, derivative with respect to eta, derivative with respect to eta, derivative with respect to eta. And then copy these. Then eta, but y coordinates. That's it. Again, I'll take basically code where you show me that you have, and I'm fine, you don't have to retype the shape functions. That one you can, for example, use from PL6. I think knowing, what to evaluate, I think that's the most important part. So I would take this as a valid answer. So that takes care of A and B. Questions? I cannot think anymore. All right. Yes.
For in general, for the exam, are we going to have a non-constant S?
A non-constant S. No. Otherwise, you will have to do integration, which I think is a little bit much. So, yeah.
For like the heat flux that you're given, when Q is positive, what's the direction outward?
When Q is positive, is outward. Yes. Any other question? All right. So let's go back to the all right, so that takes care of A and B. I forgot now what I got from this one, but that takes care of A and B, and then let's see for C. So for C, we are asked to evaluate the gradient of theta with respect to x. And so here, I don't know if I have a hint, but this you probably should check your notes from class. So if we want the gradient of, say, C code. So for C, we want the gradient of theta with respect to x. But we only have shape functions with respect to psi and eta. So how do we get gradients with respect to x when we only have shape functions with respect to psi eta? This, hopefully you can find in your notes. We need to multiply gradients with respect to psi by the inverse of the Jacobian. So this is the key thing, that if you want the gradient of theta with respect to x, you need to calculate the gradient of theta with respect to psi eta, and then multiply by the inverse of the Jacobian. So what is the gradient of theta with respect to psi eta? This one is going to be the sum of the derivatives of the shape function. So you can either write as this times the nodal values, or in the two components, this is basically the sum of the partial of the shape functions with respect to psi times the nodal values, sum of partials of the shape functions with respect to eta times the nodal values. So again, that would be the gradient with respect to psi eta. This is the one that I can calculate directly because I have shape functions in terms of psi and eta, so I can get derivatives with respect to psi eta. And the same as usual, sum of shape functions, or in this case, derivatives of shape functions times nodal values. Again, I'll do it with code because I don't want to write out all the shape functions. So again, I'll go back to here. And then I want to get gradient with respect to psi of theta. And that one will have two components. The first component is the sum of the derivatives with respect to psi times the nodal values. I'm just going to copy this because it's a little bit simpler. So I need this. This is going to be the first entry. And then instead of the x's, now I need theta 1, theta 2, theta 3. And I still need to define those values. Well, these are the nodal values of the theta. That's the first row. And then the second row is going to be the same, but derivative with respect to eta instead of psi. So everything the same, but the derivative with respect to eta. So again, sum of the derivatives of the shape functions with respect to psi times the nodal values, and then sum of the derivatives of the shape functions with respect to eta times the nodal values. And the one thing that I haven't defined is what are these nodal values, but these are given, these are part of the problem. So what is theta 1? What is theta 2? What is theta 3? What is theta 4? So those are, just check here. Those are 2, 1, 2, 3. So 2, 1, 2, 3. Yes. And that's it. So if I do that, then what I get at the end here is going to be, just print. This is not the gradient that I want. This is the gradient with respect to the psi eta coordinates. But I'm almost there. So this is the gradient with respect to the psi eta coordinates. Now, if I want the gradient with respect to xy, like I said, all I need to do is multiply by the inverse of the Jacobian. This one I gave you, but the inverse of the Jacobian is just the inverse of the Jacobian. And then grad x theta is just the multiplication of the inverse of the Jacobian times that grad c theta. And then I'll just print that. And so this is the gradient with respect to xy. That is the answer. By the way, I just want to make sure that I did this Jacobian inverse correctly. In the minus 2.86 minus 2. Okay, so we did the Jacobian. This Jacobian is correct because I just checked that the inverse matches what I have in the exam. So. This was what I put in the exam, so I did that independently. So this should be correct. But any question about as to how we got this grad x theta? All right, so that's pretty much it for this problem. And again, whether you do it by hand or you do it with code, I'm fine either way. Just show your work in the exam. You know, whichever way you do it, as long as you show your work. So in my case, you know, I would take screenshots of that Python code that I was showing, and that would be your work. I think that was the last problem here. So we have 10 minutes left. Any specific questions that you have? Yes. Which one? Which one? Oh, the way I did it in, yeah. I wasn't looking at the mesh when I was solving it, but it doesn't matter in that as long as the nodes are number counterclockwise, you will get the same answer. So I did it indeed. I think here I have 432 and I did 243. I did 243 last time. There's not going to be any change. The only change that's going to happen is actually there's no change. So the KE is going to look a little bit different, but when you do the assembly, everything, the final stiffness matrix will be the same. So let me just show you. So the question was for, am I sharing my screen? I don't even know how I'm sharing my screen. Yes, I am sharing my screen. Let's do either way. So let's do the numbering that is done here is 432. This is node 432. And then because they are named like that, 432, that means that this is sort of the first node for the, let me call it N1, N2, and 3. By that I mean, with this notation, this will be X1, Y1, X2, Y2, X3, Y3. Whereas I'll do it, I'll put the way I did it on Monday. These are the same. So these are still 2, 4, 3, but the way I did it on Monday, for me, this was X1. So this was N1, N2, and N3 in that order, right? So for me, this was X1, Y1. This was X2 and Y2 on Monday. And this was X3 and Y3. The orange ones are the same. They are both 2, 4, 3. It's just that in this case, they are named such that it starts from the 4, and then that's why these ones are X1, Y1, X2, Y2, and X3, Y3. And then the way I did it, I named the 2 first. So for me, X1, Y1 is that top, then X2, Y2, and then X3, Y3. So when you do that, the B matrix, if you do it here, they will look different. So the B matrix, which is 1/2 times the area of, I don't remember, but this is something like Y2 minus Y3 and X3 minus X2, and so on. And this is Y2 minus Y3 and X3 minus X2, and so on. They will look different. I don't remember what the values are. Then when you do this KE, which is going to be the value of K times the area times the B transpose B, and when you do it here, K and the area are the same, but the B's are different. So at the end of this, you're going to get 2 different matrices, but they are going to have the same numbers. They are just going to be swapped columns. So let's see if I have time to do it very quickly. Because the columns of the left will have the assignment 432. So these columns will have the assignment 432, 432, whereas my assignment on Monday has 243. So my mesh was a little bit different. So my assignment was 243. I don't remember what the numbers are, but let's say that this is 1.2 25. The down 1.25 will appear here. So the numbers are going to be exactly the same. It's just that let's say that this is -1, -1. So that means that the 4, 3 here will be -1, -1. So let's say that this one is 1. So that's 3, 3. So that's here, 1. Let's say that this is 2. So then there's a 2 here. And then, I don't know, -0.5, -0.5. So 2 with 4. So -0.5, -0.5. And then let's say 0. So you would get something like this. So I got something on Monday. And then, yes, my mesh was a little bit different. So if you do it with the mesh that is here, then the K will have the same numbers. It's just going to be the shuffling because of this numbering. At the end, it doesn't matter. The global stiffness matrix looks the same because for the global stiffness matrix, what matters is basically the global known numbers that you put on the rows and columns. So at the end, each one of these will lead to the same number because when you do the assembly, what you look at is the 4 and the 4. That one will go to the 4, 4 entry here. Does that answer the question? At the end of the day, the solution is the same. Other questions? Maybe time for one more question. Yes. The format for the exam? Yes. So it's a 1.5 hour exam from the moment you start. And then I think Keio said that he figured out how to make it go past midnight. But if you can start it, 1.5 hours before midnight, I would do that. I haven't tested myself, so Keio said that he figured it out. But if you can start 1.5 hours before midnight, I would recommend. So from the moment you start, you get 1.5 hours to complete the exam. The first 3 questions are a true or false question, so they should go pretty quickly. And then there's 4 sort of problem type questions. They are very similar to this problem. So this problem has been split into 3 questions in the exam. So instead of having to do everything here, there's 3 things that you have to do in the exam. Basically, 3 of the things that you see there are exam questions. And then 1 out of the whole thing, these 3 things that I did today, 1 of them is the last question. So that's what I'm saying. For the exam, it should be a fraction of what these practice problems are. And yeah, it's open book, open notes, just no human input. You can even ask ChatGPT questions. Actually, the first 3 questions are because it's all about whether or not you know how to use the resources and whether you understand the concepts of the class. You cannot talk to each other, so no help from each other. But yeah, you can use resources that are not people. Yeah, and you show your work. I don't want to see your work. I don't want to see just an answer. I want to see your work, and it can be handwritten or it can be code. I'm fine with grading either one. Yes.
Is it like submitting one PDF, or do you need like a screenshot for each question?
No, you can do a whole PDF. That would be fine as well. Just maybe alert me. I don't know how you can alert me. Because I have to say I did not. I think a couple of people submitted a whole PDF for the entire exam last time, and then I only graded the first one, and I didn't see that it was the entire PDF. And then the other questions were empty. And then initially I had graded sort of, there's no answer for the other ones. And then they said, but there was everything there. And then I went back and checked, and yes, there was a PDF with the whole thing. So I think if there is a part where you can enter text, then maybe you can say entire exam is in this question, then you can leave all the other ones blank. But as long as there's a way of communicating that there's a PDF with the whole thing, I'll take that. Otherwise, you can split it.
Is it gonna be like last time where it's like question had this?
Yes, it's going to be exactly the same as last time. And then you can either upload screenshots for each one, or you can upload a whole PDF, as long as somehow you communicate to me that I need to check the whole PDF.